I think you should be able to write all of them out if you want to write them out. Remember, when it gets to be too big, we want to see what that. Yeah, you can do it in a line too. Yeah, we want to see what you know, how many do we have? All right. So, anyone know what it is? I mean, you can start to write them out if you want. You can write in a line, Jacob. You just got to make sure, like the end is technically. So if you're at the end, the first one would be the one to your right, I guess. So the way I kind of think about it is like there are like four spots. Remember we were talking about spots last time, right? So you have four spots in there, right? So you think about well, how many people can I put? I'll just call that the first spot. How many people can we put in the first spot? Yeah, you have four options, right? You can put person A, B, C, or D in there, right? You move on to your second spot. Doesn't really matter which one's the second one, but let's just say that's the second. Now you have what, three people to choose from, right? And then you move to the third spot and you have two people to choose from. And then when you get to the last spot, well, there's only one person left, right? Now, that's not your final answer, right? Because what's wrong with that? That's 24, right? What do we notice about that? Let's say think about what we did over here. Yeah, right. So it's exactly like this, right? So we're repeating some combinations here, right? Because it's 4 times 3 times 2 times 1. That's taking into account that those two arrangements are different when we just said that they were the same, right? So we're repeating some values here. How many are we repeating? Well, think about, just this arrangement here. How many times is this equal to another arrangement? Well, we moved it over one. You can move it over again, right? So you get C, D, A, B, and that would be the same as B, C, D, A, right? And then back to that over there, right? So yeah, exactly, Willie. You're repeating this four times, right, for each one of those arrangements. So you got to divide by four, which should leave you with six. Right. We're gonna use this notation a lot today. The top is 4 factorial, right, over 4, and that's 6. You can just leave it as 4 factorial. We're going to use a lot of factorials today. Cool. Lev made a YouTube channel. He's going to put the videos up. Thank you for doing that, Lev. All right. Any questions on that one? All right. So the last example from this section is kind of an intro to tree diagrams, which we'll do in chapter 11, I think, or chapter 10. Um, So a playoff between two teams consists of at most 5 games. The first team that wins 3 games wins the playoff. So it's just like a playoff series in sports. And how many different ways can the playoff occur? Okay, so that's like team one wins the first game, but then team two wins the second, and so on. Right. So in how many ways can that happen? Right. So we're gonna do this with a tree diagram. Once we get into 6.3 with combinations and permutations, we're gonna be able to come back and do it that way. Right, which requires a little more thinking. So let's just draw a tree diagram. So how this looks is, I'm gonna start this in the middle. Okay, so let's say the way I draw this, so this is like team one, team two. Okay, so let's say that this row here is the row where we're talking about game one. Chris, the last one, four choose four. No, four choose four is actually one. This one should be. We'll talk about the notation in a couple sections. That one's actually a permutation. All right, so for game one, all right, either team one wins, team two wins. All right, that's going to be the thing for every single game, right? One of the two teams is going to win. Let's just assume no ties. Okay, so from this left side here, right, this is the scenario where team one wins the first game. Okay, so if we go to then the second game, so game two, right, this is going to start to branch off, right? Because now you have, well, if we start with the scenario where team one won the first game, right? Then that can branch off into either team one wins. I'm just gonna put ones and twos. So team one wins the second game, or then team two wins the second game. Okay, and same thing with team two on the left, right? Either team one's gonna win the second game, or team two will win the second game. All right, so the way this is read is that, okay, if I go down this way, which we call that a branch. If we go down this way, right, this is saying that team one won the first game, and then team one won the second game. Okay. If we go down this way and say team one won the first game, but then this way is saying then team two won the second game. Okay, that's a different case right there. Okay, same thing on the right side. Team two wins the first game, team one wins the second game, team two wins the first game, team two wins the second game. Okay, so these are going to start to branch off, you'll see, into different cases, right? So now each one of these numbers from game two is going to branch off, right? So now the third game, you can say, going down that way, team one wins, team two wins, team one wins, team two, team one, team two, team one, team two. Okay. Are there any questions up to here? You'll see right now that some of these are going to end, right? So remember that the first team that wins 3 games wins the playoff. Okay. So we actually have some cases that are over, right? One of the cases is that team one wins the first 3 games, right? And it's over. All right. So I'm going to box the ones that are over. So that one is done, right? That's going to be one scenario, right? Is where team one wins the first 3. There's another one that's done also, is that team two wins the first 3, right? So that branch is done also. Right, so once you see 3 of the same number, then you're done. All right, so we're done with that first branch, but this number 2, so game 5 or game 4, all right, this number 2 can branch off into 1, 2, that 1 can branch off into 1, 2, 1, 2, 1, 2, 1, 2, and then 1 and 2. Okay, and then you check to see which ones are finished there. Right, so I got, okay, so I got 1, I got 1, 2, okay, I got 1 there. I got 3 ones, so that one is done. Okay, going along this route, I got 2 and 2, so that one's not done. I got 1, 2, 1, 1. Okay, so that one is also finished. Then I got 1, 2, 1, 2. That one's not done. I got 1, 2, 2, 2. That one's done. 1, 2, 2, 1. Not finished. But that one was. That one will be done. This one will be finished. And that one will be finished. Okay, so the boxes are all the ones that are finished. Yeah, you're gonna get 20. Yeah, the box numbers means that we're finished with that the game, right? The team that wins 3 games in a row wins the whole thing. Okay, and the last game, we know there's only going to be 5 games, so game 5. Okay, so branch off the last ones that aren't finished, so like this one. So I got a 1 and a 2. I got a 1 and a 2. This one, a 1 and a 2. Sorry, that one's kind of messy. This one, I got a 1 and a 2. 1 and a 2. A 1 and a 2. Okay, everything that was still available for game 4, right, on the second to last row, that was all the ties where each team had a same number of wins, so they had 2 wins and 2 wins. So whoever won this last one in game 5 wins everything, right? So all of these are finished. Right, and I think someone said, so you count up the number of boxes, there should be 20. So 20 possible outcomes. Okay, and there is a faster way to count these, which we'll see. It's a little bit trickier though, because some of these are tricky to count. Okay, but that's an example of a tree diagram. All right, any questions on that one? All right, so that's the end of 6.1. Uh, 5 factorial over 3 factorial. Almost. Which I guess, actually, I think you're close though, Chris. I think I know what you're trying to say. But yeah, we'll come back and do that one. All right, so let's move on to 6.2 then. Okay, so remember this whole chapter is about counting. Okay. Now the first thing, or I mean, this section is labeled pigeonhole principle, which we've talked about pigeons and holes, right, in the function section. So in 2.3, what the pigeonhole principle is. So if you have a positive integer and k plus one or more objects into k boxes, right? So that's like saying you have 10 pigeons trying to put into 9 holes, right? Then there's at least one box containing 2 or more pigeons, right? Or objects. So you got 10 pigeons, 9 holes, right? You can fill up all the holes. You still have that one left over that you got to throw in somewhere. Okay. And that corollary says, well, then it is not, we know that to be not one to one. Yeah, it's like that. At least 2 people have the same birthday. Okay, so that's all the pigeonhole principle says. Okay, so the birthday one is, that example that Misael's talking about. So what can we say about a group size of 367 people and their birthdays? Right. Well, there's 367 people. Worst case scenario is that everybody has a different birthday, right? You know there are 366 possible birthdays
So why did we put 366?
because there's 366 possible birthdays, isn't there? Because there's 366 possible days.
365, isn't it?
366 with leap day.
What's that?
With leap day,
Oh,
February
okay.
29th. Yeah. So we always
I
forget about
like,
February 29th. That's
gotcha,
leap
gotcha,
day.
gotcha. I got it.
Yeah. All right. So if we have 367 people, then we know that at least 2 people have the same birthday. All right. So that's pigeonhole principle, right? This next example is also an application of that. So how many students must be in a class to guarantee that at least 2 students receive the same score on the final exam? The exam is graded from 0 to 100%, and the score must be an integer. Okay, so now half points. Okay, so how many students have to be in that class to guarantee that 2 students will receive the same score? Yeah, that's right, Barry. It's 102 students, right? Because again, worst case scenario, let's say everybody gets a different score, right? So someone gets 0%, someone gets 1%, 2%, 3%, 4%, all the way up to 100%, right? Well, between 0 and 100, there's 101 different options, right? So there's 101 possible scores. So I mean, worst case scenario is that everybody gets all those different scores, right? Well, then that 102nd person, right, has to be in one of those 101, right? There's no other options, right? So you need that 102 students. All right, so you need 102 students for that to happen. Any questions on that one? Yeah, because JP, you want to know what you want to guarantee that at least two students have the same score, right? So for it to be 100% like guarantee, you gotta have 102 students, right? You can't say like you can't say 101 students, right? Because then you have the case where everybody has a different score, right? That's not guaranteeing that two people will have the same score. That makes sense? Cool. All right, so we have a different form of the pigeonhole principle. So if you have n objects placed into k boxes, then there is at least one box containing at least, remember this is the ceiling function or the roof function, however you want to think about it. I think it's called both roof or ceiling. Ceiling function. Remember, you take the integer, the next integer up. Okay, with n over k objects. All right, so we'll see that right now. Okay, so with 100 people, at least how many people were born in the same month? Okay, so I mean, if you use this, theorem, we got a 12 divided by, that's the number of boxes, right? In this case, my boxes are my months, right? So we have 12 boxes, 12 months, or sorry, no, backwards. N objects, my boxes are my months, but that's my denominator. My objects are my people, so that's 100. Right, divided by 12. What is 100 divided by 12? That'd be 8 something. It's about 8.33. Right, remember the ceiling function takes it up to the next integer, so you get 9. Right, so you're gonna have some months, you gotta have at least 1 month with 9 people. Right, because remember, you can think about this worst case scenario again, right? To start splitting up the people into the months. So let's say person 1 is January, person 2 February, person 3 March, and so on. Right, and then you got to eventually come back and repeat, put another person in each month, come back. Right, so it's like you're going up by 12s, right? So you got like 12, and then 24, and then 36. Right, you'll get all the way to 96. Right, and there should have been 8 of these. So 8 times you have to go back and put people in, right? You got those 4 leftovers that you got to throw into boxes that already have 8 people, right? So you have some with 9. All right, we're gonna see a couple more of these examples. So the generalized pigeonhole principle. Okay, and honestly, I mean they're theorems, but if we just kind of talk through them, you can figure them out without having to use the formulas. So how many cards must be selected from a standard 52 deck to guarantee at least 3 cards of the same suit? Okay, so remember the suits are the shapes of the cards, right? So you got diamonds, hearts, spades, and clubs. Okay, how many do you have to pull to guarantee 3 of the same suit? All right, so why don't you guys take a second? Why don't you read through both of these examples here and see what we think? I see one answer, 12, and then I see Chris change it to 9.
Not exactly.
What was that, Richard?
Sorry. I think I got unmuted for a second.
Oh, okay, for sure. Yeah, it should be 9. Well, so yeah, you should get 9 for this one. Okay, now if you use the formula, right, you're trying to find, what is it? N over K, right? Now in this case, you're trying to find how many cards you need, right? So you need to find N, right? K is the number of boxes, right? In this case, your boxes are your suits. And there are 4 suits, so 4 boxes. You need that to be, you want at least 3 cards of the same suit, right? So you need that to be greater than or equal to 3. Okay, what number is going to give you that, right, with the ceiling function? Well, if you do 8 cards, you get 8 over 4, which is 2. Ceiling of 2 is still 2, right? So you need the next number, which would be 9. Okay. Now, typically with, there's only a couple formulas I like to even use in this chapter, right? Because I think it all just comes from just thinking about it and, kind of reasoning through this, right? So let me say that, I got my 4 boxes, which are my 4 suits, right? So I got hearts, I got clubs, right? I got spades, it's an ugly spade, does something like that, right? And then like that, and then I got diamonds. Okay, I have my 4 boxes. All right, so I want to guarantee at least 3 of the same suit. All right, so think about your worst case scenario. So let's say I pull a card, it's a heart, right? I pull a card, and then it's a club. And I'm just gonna put dots for the cards being pulled. I pull another one, it's a spade. Pull another one, it's a diamond, right? I don't have 3 of the same ones, right? So let's go through again. All right, so put a dot in each, right? That right there is worst case scenario, right? Where I pull out 8 cards and it's just 2 of each. I haven't got my 3 of one yet, right? But this 9th card, right, has to go. It has to be one of these 4, right? So no matter what it is, right, we know we need 9 to guarantee it. Right, so typically with these, when you talk about guaranteeing, think about your worst case scenario. All right, any questions on that one? All right, so the next one, how many cards must be selected from a standard 52 card deck to guarantee that at least 3 hearts are selected? Okay, so just think about this logically, work through it. You're close, Andre. Think about your worst case scenario. Yeah, you're good, Barry. So what is your worst case scenario, right? Well, worst case is that, I pull everything out before I even get 1 heart, right? So that would be like pulling out, we're dealing and I pull out 13 clubs. And there's 13 of each, 13 diamonds, 13 spades, right? I haven't even pulled out 1 heart and I pull all those other ones out, right? What is this, 39 cards? All right, so I pull out 39 cards. Worst case, right? Worst case scenario. I pull out all 39, nothing's a heart. Well, what's left? It's only hearts left, right? So you know for sure after you're gonna have hearts being pulled out, right? You need then at least 3. So you still have to pull out 3 of those hearts. So you get the 39 plus the 3, which gives you 42 cards. The ceiling function one. So I don't think you can apply it to this one. You would need. Yeah, let me think about that, Barry. I'll get back to you on that. Oh, speaking of getting back to you, I figured out that when we were talking about the other day, Derek, we can go over during break of the problem you asked about the counting one. All right, yeah, let me think about that one, Barry. I was thinking about it right now, actually, how to apply it. But yeah. All right, so let's do. I think this is the last one. Yeah. So we got the last one from 6.2. So what is the least number of area codes needed to guarantee that the 25 million phones in a state can be assigned distinct 10 telephone numbers, right? So just like with any phone number we've ever talked about, right? They have to be different. Phone numbers are of the form and then YXX, YXX, XXX, X. Y is between 2 and 9, and X is between 0 and 9. Okay, so you have 25 million phones, and you have, so you have 25 million phones, so 25 million phone numbers. How many area codes do you need, right, for all those to be distinct? Okay, well, the phone numbers are YXX without the area code, right, are in this form here. Okay, I want to know how many area codes we need, right? So let's just look at the numbers, right? In a sense, you want to look at how many times the numbers repeat, right? That'll tell you how many times that, how many area codes you need, right? So if they repeat twice, then you need 2 area codes, right, to change those numbers to be distinct. All right, so how many possible numbers, phone numbers, are there of this form? Right, so 1, 2, 3, 4, 5, 6, 7. All right, so I'm gonna do my spots again. All right, well, how many options do I have for this first number, which is my Y? How many options are possible for Y?
8.
Yeah, it's 8. Right between 2 and 9, there are 8 numbers: 2, 3, 4, 5, 6, 7, 8, and 9. Okay, what about for, so all the X's are going to be the same number of options, right? How many options do we have for an X?
Is it 10?
It's 10. Right, so all of these are 10 options each. So if we multiply those, we get 8 times 10 to the 6th power. Okay, this comes out to be an 8 with 6 zeros, so 8 million. Okay, so you can make 8 million different phone numbers. Yeah, you're right, Chris. In
I
that
have a
form.
question.
Yeah.
So why did we raise the? So why do we have the 10 to the power of 6?
Because you have 10 times 10 times 10 times 10 times 10 times 10.
1, 2, 3, 4, 5, 6. But we had another y in the form of the phone numbers.
Yeah, those three numbers are the area code, right? So we're trying to see how many of those we need, right? So we're
Right.
only looking
Then-
at that set right there.
Okay, I see.
Yeah, cool.
Got it. Thank you.
Yeah, so we have 8. So those numbers can be rewritten in 8 million different ways, right? But we have 25 million phone numbers, right? So, I mean, if you think about it, this is the 25 million divided by the 8 million, right? So you need, like Chris said, that's 4, right? Because if you have 3 area codes, right, that'll change each phone number into 3 different options, right? That's only going to give you 24 million. You still have a million numbers that left, so you need 4, right? You need that one above. So we need at least 4 area codes. Right? And it's at least, you can have 5 area codes, right? You can have 6, 7, 8 if you want. All right. Any questions? That's the end of 6.2.
So my question is not about the class. I mean, it's basically about the class, but until what time does the class today is gonna last? Until 2:35?
So it's, yeah, just like the same, 235.
All right, for sure. Thanks.
Mm-hmm. All right. Any other questions before we move on to 6.3? So these are I think they're very fun questions, interesting sections and everything. All right, so let's do 6.3 then. Okay, so 6.3 is talking about combinations and permutations, and we'll talk about what the difference is between the two. Okay. Yeah, so why don't you guys take a second and try these 2 examples. Okay, so the first one, in how many ways can we select 3 students from a group of 5 to stand in a line? And how many ways can we arrange all 5 of those students? So 2 different parts on there. The second one, how many different committees of 3, so like groups of 3, can be formed from a group of 5 students? Definitely don't try to count these up. The first one, you can probably do the second example. But the first one, I think the numbers are big. Careful with the second one, Willie. Is the 5 factorial for the first example or the second example? Oh, okay. Then yeah. I thought it was for the second example. All right, so let's think about this, okay? So I'm gonna just label this like part A and part B. So part A, and how many ways can we select 3 students from a group of 5 to stand in a line? Okay, so to stand in a line, you got 5 total students. You're picking 3 of them. Right, how many options for the first spot?
5,
5, right? How many options for the second spot?
4,
4. And then 3 for the last spot. All right, everyone cool with that? So this is 60. We're gonna have this in notation for us right now. Part B, how many ways can we rearrange all 5 of those students? So now you got all 5 of them standing in a line, right? So it's the same idea, right? You got 5 options for the first spot, 4, 3, 2, and 1, right? That right there is a 5 factorial. All right, any questions on that first one? I'm gonna go back and do it with combinations and permutations. But you know, that's the thinking behind it. Okay. The second one, how many different committees or groups of 3 students can be formed from a group of 5 students? All right, what do we think about that one? You're close, Michael. Yeah, you're right, Barry. So let's think about this, right? You're picking a group of 3, right? So it's like you have your 3 spots. Okay. So for the first part, you got 5 students to choose from, and then 4 students to choose from, and then 3 students to choose from. Okay. Now this is not the answer. Okay, this is part of the answer, but it's not the answer. Okay, because the difference between this problem and the one above, right? And the one above, you're rearranging them in a line, right? So you know, if someone is in the first spot, and then someone else is in the second spot and you switch them, right? That makes a different line, right? Now, in this case here, if I pick, I'm going to use the last three names on chat. So if I pick Michael, Joel, and Barry, that's the same as me picking Barry, Joel, and Michael, right? It makes the same group, right? Whereas if we're lining them up, switching two of them makes a different line, right? You guys see the difference there? All right, so in the second example, we actually have some repeats in there. Okay, how many repeats do we have? Right, well, the repeats come from, okay, so I've made my three, right? So I picked Michael, Joel, and Barry. All right. So, 5 options, 4 options, 3 options from a group of 5, right? This is my group though, okay? How many repeats do I have? Well, the repeats come from how many ways can I rearrange those 3? Right, well, I can rearrange them in the form of, well, I got 3 options for one spot, 2 options, and then 1 option. Okay, so you actually have 6 repeats in there, or 6 times the repeats. Right, so you actually got to divide by that amount. Right, and that comes out to be 10. Yeah. All right, so in this first case, in the order that the students are in, it changes it, right? So we say in this case that the order matters. Right, in this case, we're just picking the group of 3 students, right? In the order that I pick these 3 students in, it doesn't matter, right? Doing it in this order is the same as like if Barry goes first and then Joel and then Michael, right? So in this case, the order doesn't matter. Oops. Okay, and we have special names for those. Okay, when the order matters, that is called a permutation. Okay, when the order doesn't matter, that's a combination. Okay, the notation for that, so like let me do part A, is a capital P for permutation. And then parenthesis, your first spot is how many total people you're looking at. So in this case, 5, comma, how many are you picking from there? Which I picked 3. Okay, this one, the part B would be P5, comma 5. Okay. With combination, it's a C. Okay, and then we have 5 people, we're picking 3 people. Okay, so the C and the P are differentiating combination and permutation. Okay, order matters, order does not matter. Combination, I think, is the more common one. It has a couple of notations you'll see. So you have this form, Barry did it in a different form, right, which is that, and the last form is like that. Okay, so you'll see all 3 of those. Permutation just has that one with the P. And I have the formulas for that are right below. Your calculator also has the power to do these in your calculator. If you go on math on your calculator and you go over to PRB, probability, you'll see numbers 2 and 3, right? Look like this form. Okay, but when it comes to these, you can just leave it. I'm okay with you leaving the answers in these forms. You don't have to do all the work to it. All right, any questions on either of those? All right, so I have the formulas here for you. So with permutations, you got n factorial over n minus r factorial. And with combinations, you got n factorial over r factorial times n minus r factorial. Now notice that the difference is that r factorial in the combination one, right? Because that r factorial gets rid of your repeats. Okay, that's why you have that extra one in there. Okay, so they're almost the same formula, just with that r, right? So like if I did in this form here, right? So we said that's 5 choose 3. So that is 5 factorial over r is 3 factorial and 5 minus 3 factorial. So that's 5 factorial over 3 factorial times 2 factorial. Okay, and you get the same exact answer. Okay, because you get a number factorial 5 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 is 2 factorial is 2 times 1. You'll see that that 2, that 1, that 2, that 1, and we have exactly what we had above. Okay. So I mean, you don't really have to plug these in, but I mean, just so you can see that, you know, the way you think about it matches up with the formula.
A quick question on the verbiage. I heard you say 5
Yeah.
choose 3. Is that how
Yeah.
you would say both the combinations and permutations? If you're speaking
So
about
when
that
I say
format?
choose, yeah, it's a good question. When I say choose, I'm talking about combination. With permutation, I'll probably say permutation of, and then like 5 choose 5 on that. So with permutation, I'll emphasize permutation. With combination, I just say choose.
Okay, gotcha. Thank you.
Mm-hmm. The last thing you got to be, you know, careful of is, you know, with this one here, with the 5 choose 5, you know, what the formula says is n factorial over 5 minus 5 factorial, right? That's a 5 factorial over 0 factorial, right? You guys know what 0 factorial is?
1.
Yeah, it's 1, right? So you get 5 factorial over 1. Okay, so 0 factorial is 1, right? And that just comes from the pattern. There's a nice pattern to those. All right. If we have time today, I'll show you the 0 factorial equals 1. But all right. Why don't you guys go take 10 minutes then, and then we'll come back and finish. All right, so yeah. All right, Derek, you want to hear the explanation, or did you go take a break? Okay. So you had the 10 and then times 36 to the 5th. Okay. So the problem with that is okay, so you're saying your number is in your first spot, right? But then you have to account for the number possibly being in other spots, right? Which is you know, when you have the 36 options, you have a possibility of it being there. Right? You got to make sure that for sure you have it in the other spots, right? Just one digit. But what happens is you can't multiply it by 6 because then you start to overcount things, right? And I did the math on it, and it actually doesn't come out to be like a nice, you overcounted by like a nice whole number, right? It actually is some kind of crazy decimal. Okay, so yeah, it's like when you put the 10 in the first spot, that means your number's in your first spot, but you're leaving the possibilities of numbers in other spots, right? You can't do that times 6. Yeah, it's a little weird, right? So anytime it comes to like counting for at least things, you gotta be super careful. Yeah, for sure. All right, so let's keep on going. You guys want to take? I'd say take a minute or two and try these. Just leave it in combination permutation form. Okay, you don't have to multiply it out. The trickiest one, I think, is the fourth one, which is this right here. All right, so why don't you guys take a minute or two and try those. As you're going through these, think about, does the order matter? If it doesn't, then it's a combination. If it does matter, then it's a permutation. All right, so it's cool if you're not done. I just want to make sure we get through at least this section. So 5-card poker hands. So we are, you're being dealt 5 cards from the 52 cards. Yeah, those look pretty good, Willie. I think good. So think about, does the order matter? Does the order not matter? But when you're getting, dealt cards in any game that you play, usually the first thing is you start rearranging them yourself, right? Does that change the hand you got? No, right? So the order doesn't matter. Right? So this is a combination. Right? Combination of, well, we have 52 cards to choose from, right? And we're picking 5 of those cards. All right, and then I'm just gonna write it out so you can see the so this is r factorial 52 minus 5 factorial. Right, because I want to make a point with part the next part factorial times 47 factorial. Okay, so this is 2,598,960. Right, so that's how many possible just 5-card poker hands there are. All right, so you ever get like a royal flush? I mean, you're really lucky. All right, for the next part, so how many ways are there to select 47 cards? So it's you still have your 52 cards, but this time you're picking 47. All right, the order still doesn't matter. So writing out, with the formula, you get 52 factorial times 47 factorial times 52 minus 47 factorial. And you should notice something about this number, right? It is the same as what you had above, right? These two numbers are the same. Can you get a lot of that happening with combinations and permutations? Okay, at the end of 6.4, you'll see us build Pascal's triangle, and you see where they are the same. Okay. All right, any questions on those two? Feel free to ask. Typically in class, when it's quiet and I ask if there's any questions, I can tell by your faces if there is questions. Can't tell by your faces right now and in silence if there's questions or not. Okay, so just let me know if you do have it. If you do have any questions. All right. The next example, so you have a first prize winner, second prize, third prize from 100 different people. All right, how many ways can you select those three? Well, in this case, does the order matter? Well, picking, in this case, who would my three people be? So if Willie was first place, Derek was second place, and Joel was third place, well, that's different than if Joel was first, Derek was second, and Willie was third. All right, so the order matters in this one. All right, order did not matter. Order doesn't matter. All right, same thing with that one. So in this case, the order matters, right? So we need a permutation. All right, we have 100 people to choose from, and we are picking 3 of them. Okay, so you get a permutation of 100, choose 3. All right. The next one, actually, let me do the last one. We'll go back up to the letters one. I think that's probably the hardest one. So in this one, so a group of 30 people work for a company, and they need a crew of 6 people. Okay, how many crews can we make, assuming that all the members have the same job? Okay, so if they have the same job, the order doesn't matter, right? Because they all have, in a sense, the same title. Right, so that'd be combination. You have 30 people and you're choosing 6 of them. Okay, but for the second part, if they had different jobs, right, that's like the example we did before where like there was a first place, second place, third place winner, right? In this case, the order does matter, right? Because they have different titles. So that is a permutation of 30 choose 6. And those are different numbers. Right? Remember, with combination, you divide out the repeats. All right. Now going back up to this letter one, you know, how many permutations of the letters A, B, C, D, E, F, G, H can contain the block A, B, C? So that means that A, B, C have to be stuck together in that order. Okay. Well, if they're stuck together in that order, in a sense, they're like one letter, right? You can just think about that as like one letter, one spot, right? So before, you know, if we do the spot thing, right? We had, you know, we got one spot there, one spot there, one spot there, one. This last ABC is like one spot, right? Because that ABC will be together, right? So you can think about it that way. Right, so ABC is one spot, right? Because they're stuck together. So in a sense, we have how many spots now? We got 1, 2, 3, 4, 5, 6. We got 6 spots to choose from. Right, so for the first spot, you got 6 options, right? You can either put all of ABC there, you can put D, you can put E, you can put F, you can put G, you can put H. Right, and then you get 5 options, 4 options, 3 options, 2 options, and 1 option. So you get 6 factorial there. Right, to see this in like permutation form, right? Because it says permutation. Well, you know, it is permutation because the order matters, right? Putting ABC in the front is different than putting ABC at the end, right? Well, you still have to kind of think about it as spots, right? You have 6 things to choose from, right? And you're picking all 6 of them, right? That is 6 factorial over 6 minus 6 factorial, which is 6 factorial over 0 factorial, which is 6 factorial over 1, which is 6 factorial. So you get the same thing in both cases. And you know, you could have thought about this different ways, and that doesn't mean you're wrong, right? As long as it comes out to be 6 factorial, which is a pretty big number, right? Then you're good. Any questions on that one? Okay. Then last page. So the last couple examples talk about anagrams. So anagrams are like rearranging of letters. So like we did in the one we just finished, rearranging letters. Typically it's to make words, right? How many words can you make from those letters? So like M, A, T, and H. How many words can you make from there? Just for the sake of this being a math class, let's just include every possible like option, even though it's not an English word, you know, so like MTHA, right? Not an English word, but it's a rearrangement of the letters, right? So we're gonna include those. All right, so how many anagrams can we have with the word math? So how many ways can we rearrange those letters? Think about the way we just did the other one. Yeah, Barry, you're right. Andre, not combination, because in this case, the order matters, right? Putting, you know, having this group is different than having that group, right? By changing the letters you're picking, right? So this is a permutation of 4, 4, which is 4 factorial, right? You can also see it as 4 factorial because there are 4 spots, right? 4 letters, 4 spots. Well, I got 4 options of what I can put in the first spot, and then 3 options, right? And then 2 options, and then 1 option. That is 4 factorial. All right, you good, Andre? You see why it's a permutation, not combination? Cool. All right, the order matters in there. Okay. Now, what about the word Mississippi? No, just the 4-letter ones. So yeah. Yeah, we're not doing anything like 1-letter one. It's just rearranging those 4 letters. Yeah, in Mississippi, you have repeating letters, right? You got S's, you got 4 S's, 4 I's, and 2 P's, right? So how does this work? How do we get rid of those repeats, right? Because when you think about, rearranging this, right? So let's say, I have this original word, Mississippi. But what if I write that and say that, well, I actually switched those 2 P's to get that next one I had. But when it's the same rearrangement, right? I don't see a difference in there. That's where you start getting repeats, right? You can't tell the difference between all of the S's, all of the I's, all of the P's, right? Now, if each one of those S's was like a different color or had some kind of thing in there to differentiate the 4 S's, then that's different. But in this case, we can't tell the difference between the S's. We can't tell the difference between the I's. We can't tell the difference between the P's, right? So we got to figure out how we're going to get rid of those repeats, right? In this case, there are 11 letters, right? So you think about your 11 spots, you would have 11 times 10 times 9, all the way down to 1. So it would be 11 factorial if all those letters were different, right? We have repeats though, right? So how do we get rid of the repeats? We got to divide something out. All right, so let's start with the first letter, I. Right, you have 4 I's in there. How many ways can you rearrange those 4 I's? Yeah, 4 factorial, right? It's like if you just look at the I's, right? You can't differentiate the I's, so we got to divide it out. Well, how many times would we have rearranged those I's? Well, there's 4 of them, right? So I would have had a 4, a 3, a 2, and a 1. So you repeated those I's by 4 factorial. Okay, those S's, there's also 4 S's, right? How many ways to rearrange those 4 S's? Well, same, 4 factorial. Right. And the last repeating is what is it? The 2 P's. All right, how many ways to rearrange those P's could you have? Yeah, 2. And just to keep it consistent, it would be 2 factorial, which is 2. Right, because you would have 2 options for the first spot and then 1 option for the second spot. Right, and this is how many there would be, right? Using all 11 letters. Right, like Chris asked if this includes less than 11 letters, it doesn't. All right, any questions on that problem? This one actually has a different notation with combination and permutation. What is it? Shoot, give me 1 second. It has a different, because it should have, I think if I remember correctly, the way this one looks is 11, 4, 4, 2. I think it's something like that. It's a weird notation. Yeah, it's like that. Dividing the overlap, it's because you're typically when you repeat, right, you divide it out. You have that nice factor. It's usually division. I think you're probably thinking of the password one that we did the other day. That was because you were counting the at least part. When we talk about at least, you'll see right now in the next example, right? Typically that's like addition and subtraction. Yeah, so I mean, even to stay more consistent, this would actually also be divided by a 1 factorial because of the m, right? How many ways to rearrange the 1? Or that 1m is just one way, right? So you'd actually have another 1 in there, but it's totally fine without doing that. All right. So last example then. So a coin is flipped 8 times where each flip comes up either heads or tails. Okay, so how many possible outcomes are there in total? How many contain exactly 3 heads? How many contain at least 3 heads? And how many contain the same number of heads and tails? Okay, so you're flipping a coin 8 times. All right, let's just say it's fair and it's heads and tails. Okay. So, I mean, this is like 8 spots, right? Because you did it 8 times. Right? Well, how many options do you have for the first spot? Yeah, you have 2. Right? 2 for the second, right? Heads or tails? Heads or tails. 2 heads or tails, heads or tails, heads or tails. Right? For all of these spots, that's 2 times 2 times 2. That's 2 to the 8th power. All right, how many contain exactly 3 heads? And you can just give it to me in notation. You don't have to give me the number. So how many possible outcomes contain exactly 3 heads? I see a bunch of different answers. Yeah, so does order matter or does it not matter? So if you have your 3 of them being heads, right? You pick that group with 3 being heads. Does it matter the order in which that they were heads? It shouldn't. All right, order does not matter in this. All right, so you have a combination. All right, you have 8 spots. All right, you got to pick 3 of them to be heads. Yeah, I think that's 56. You choose 3. All right, any questions on part B? No, so it's saying like you can have, so yeah, that's one option. Heads, 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 and the rest tails, but you can then have heads, tails, heads, heads, and then everything tails. Right, you have your 8 spots. 3 of those have to be heads. Without the factorials, oh, with the factorials? Yes, I mean, this is 8 factorial over 3 factorial times 8 minus 3 factorial. So what it's saying is, Willie, was when you choose those 3 things to be heads, right? I mean, that's like you're picking your group of 3, right? Mixing those 3 up, that order doesn't matter. The 3 heads. Right, and since you're picking the spots, right, you're just kind of picking where those spots would be. Yeah, it's like the labeling, right? So it's like your 3 spots that you're picking to be heads, they're all labeled with H, right? It's not like a red H, a blue H, a green H. All right, any other questions on that one? No, it doesn't, Andre, because part 1 is just all your possible ones. Yeah, it's not 3 heads in a row, GP, it's just 3 heads in total. Right, you can have a head on the first one and then like in the middle and then one at the end. Any other questions? All right. Part C then. So how many possible outcomes contain at least 3 heads? Okay, so you can have 3 heads, you can have 4, you can have 5, you can have 6, you can have 7, or you can have 8. Right? That's what at least 3 means. Okay. Now, what operation am I going to use to put all those together? Right? At least 3. So I can have 3, or I can have 4, or I can have 5, or I can have 6, or I can have 7, or I can have 8. Yeah, it's addition, right? Because to have at least 3, right? So how many ways can we do it with 3? Well, we just did that in part B, right? That was 8 choose 3, right? Plus, how many ways can we pick, or can we choose there to be 4? Well, that would be 8 choose 4. Yeah, all the way to 8 choose 8. Plus 8 choose 8. And I have no idea what that comes out to be, but right, just seeing that you have, remember with at least, that's the tricky one, you have to break it up into pieces, right? Because at least 3 is, well, it's 3 or 4 or 5 or 6 or 7 or 8 of them. You see why it's not permutation, Chris? Cool. All right, any questions on that one? All right, the last one, how many possible outcomes contain the same number of heads and tails? All right, so you gotta have the same number of heads and tails, so how many of each do you have to have? 4, right? So you gotta just, you can think about picking where you're gonna put the 4 heads or where you're gonna put the 4 tails. Yeah, exactly, Willie. So it's, you got 8 options, you gotta choose where 4 are going, right? So either you're picking the heads or the tails to be those 4. The top part of combination. You're talking about part A, Andre? Yeah, so part A is your just total possible outcomes. Right? It's not specifically saying like how many heads or tails you have to have. It's just all your possible outcomes. So if you were to like list out, you know, all of the possible things you could have with this, with these 8 spots, that's how many there would be. Right? What B, C, and D are doing is, you know, looking at part A, you know, your whole list of all these outcomes and looking at, you know, part B, exactly 3 heads. How many of all those outcomes have exactly 3? So as you'll see when we get to probability, you know, you'll see questions like, what's the probability that, you know, you flip the coin 8 times and you get exactly 3 heads? Well, like all your possible outcomes, this right here would be your denominator. This would be your numerator. Because the 2 to the 8th is all your possible outcomes. Okay, where part B, it's not looking at all your possible outcomes. Right, the 8 is looking at the 8 spots and how many you're picking from there. Yeah, so I mean, you know, where this is coming from, let me do it like how we did the first 2 examples in this section. We didn't even have this formula yet, right, with combination and permutation. So I mean, you have your 8 spots, right? You have you got to pick 3 of those to be heads, right? Well, how many spots do you have to choose from for, let's say, the first coin to be heads? Well, you got 8 spots to choose from, right? You can pick any of those 8 spots for the heads to go in. And then, you know, used up a spot. So the second head, you have 7 spots to choose from, and then 6 spots to choose from. Right? So let's say I threw the heads, like, let's say I did it here, here, and here. Right? I had 8 options, then 7, then 6. Right? The thing is what, you know, Willie was asking is, does the order matter? Well, isn't that the same arrangement as if I flip those two? Right? So you got to divide the repeats. The repeats are, well, how many ways can I rearrange those? Well, I can rearrange them in 3 times 2 times 1 ways, right, to get rid of all your repeats. And this is the same exact thing as your formula. It's just the formula is, you know, in a nicer way, but that's in a sense how they're all working. Cool. All right, so the last 2 things from this section that I wanted to mention were, you know, we're going to see this in the next section. So this is like combination of n choose n. Okay. Do you guys know what that is? Where n is, you know, a positive number? How many ways can you, so you have a group of things, how many ways can you pick all those things? Yeah, it's one way. And then the other one, you have a group of n things, how many ways can you pick 0 things from there? Yeah, so let's say, I mean, look at the stuff you have in front of you, right? Just a group of, you guys probably have papers, pencils, right? Just say that's however many things. How many ways can you pick up none of those? Well, it's one way by, the one way is not picking up anything. All right. And okay, so let me, how much time we got? We only have 10 minutes. 6.4 is binomial theorem, which I cannot cram into 10 minutes. So let me, we have some, I guess, a little bit of extra time. We're pretty much on schedule. We're only 1 section behind. So I think we'll be good with finishing everything in the semester. Actually, let me take a second and talk about 0 factorial being 1. Okay. So let me write out some of these. So 1 factorial we know is 1. Yeah, you can think about it that way. So 1 factorial is 1. Now the thing about math is, you know, there's patterns in everything in math. And, you know, on when I see you guys back again on Monday when we do 6.4, you're going to see a lot of like things in Pascal's triangle that are coming up everywhere. So 3 factorial is 3 times 2 times 1. Right, that was 2. That is 6. 4 factorial, that's 4 times 3 times 2 times 1. So you have another factor of 4. Right, so that's 24. Right, we can even do 5 factorial. Right, so you get 5 times 4 times 3 times 2 times 1, which is something I should know. I think it's 120. Yeah. Okay. So look at patterns. All right, going down the line, you're multiplying by the next integer, right? What about going back up the line? Well, if we multiplied to go down the line by the integer, going back up, we're dividing, right? So we divide by that 5, right? You see that extra factor of 5 is gone, right? Going up. Go from 24 to 6, you divide by 4, right? And then divide by 3, right? Divide by 2, right? And then going up one more, we divide by 1, right? So just like factorial, right? As you move up the line, you're multiplying by that next integer, right? So to go backwards, right, opposite of multiplication is division, right? And then you divide by that number. You guys see the problem with trying to go back up another step? Yeah, then you start dividing by 0, right? Which, yeah, typically, when you're dividing by 0, you're talking about infinities or negative infinities, right? But that's the reason that 0 factorial is 1. Now, the other way to think about it is, in a sense, when you're talking about factorials, we built this, let me see, when was the last factorial? So this way here, right, we did factorials in this problem. All right, we're talking about rearranging 4 things, and we got 4 factorial, right? It kind of goes with, this example here. This is saying you have 0 things. How many ways can you rearrange 0 things? Right, and you can do that in one way, right, by just leaving exactly how it is. Okay, so that's 0 factorial. All right, any questions? These problems are pretty fun. As you'll see when I see you guys, not this Monday, but next Monday, we're gonna do 6.4, which is binomial theorem. So the last section we'll do, I think for you guys' I haven't decided what your next discussion is. I'm thinking I'm gonna make the video for you guys to sign up for Overleaf probably after your test. That way you don't have to worry about it before your test. So I think for your next discussion, I might throw in some cooler problems doing this. So actually, let me go back and, at the beginning, we started writing out what we were gonna put on our exam. Okay, so we're gonna do 6.2 and 6.3. Okay, so only up to 6.3. 6.4, we'll throw it on the next exam. Okay, so this is definitely stuff you wanna, take a look at. 2.3, 2.4, 2.5 probably felt like ages ago. I'm hoping the quiz that, I gave you guys last week will hopefully review some of that stuff. I'm gonna send out solutions to that sometime this weekend. So you'll have solutions to that. Your quiz will be due sometime next week. That way I can send you out solutions next week, right? Before, or that way you can study if you want to start studying. All right. I will be available over the break if you guys have any questions, right? We don't meet as a class, but I'll still be available if you want to ask questions. I won't have like official office hour, but if you want to hop on here for office hour, just let me know. You guys are studying and things like that. All right. You'll also have a new homework assignment on this stuff here on chapter 6. Okay. Y'all have any questions? All right. Well, I hope you guys have a good, safe spring break. Stay healthy. try to enjoy it, I guess, as much as you can. Really, you can't really